Hello! In this video we're going to talk about integration with partial fraction decomposition as a technique. So I'm just going to go through it step by step using an example. And the first step, well, let's first say what sort of case you would want to try this technique. It's cases where, of course, your function is fractional, so it's a fraction with in the denominator something linear generally, and in the numerator something quadratic. You can use it more generally, but this is the case that I'm going to talk about in this video. So the first step will be to decompose the denominator. So, of course, in this case, I can see 24 is 8 times 3, and I can decompose this whole thing as x minus 8 times x plus 3. Okay? And of course nothing has happened in the denominator. So there you go. dx. This is the very first step. Well, so far of course this doesn't help you at all trying to integrate this thing. We have to come up with something else. And the thing to do here is the technique that's called partial fraction decomposition. Here we actually still have a product of two functions if you want. You could split it like x plus 2 divided x minus 8 times 1 over x plus 3. And you want to write it as a sum. And I'll write down here what the idea is. We want to write x plus 2 divided by x minus 8 times x plus 3 as a sum like this. And it's actually a bit of magic that we can. But the magic, you know, will follow. I will explain. It will be less magical once you see it happening. But it turns out that in general, you could do such a decomposition. If this is linear and quadratic, and you know how this is decomposed, you can actually try to split it in a sum with, one numerator, the first factor, and the other numerator, the other factor. Only, as you just noticed, there are two unknowns here, the a and the b. I don't know how to choose them so that this is actually true. So it seems like we have an equation to solve, and the weird thing, there are three unknowns in this equation. There's x, there's a, and there's b. So how are we ever going to solve it? But the nice thing is that there's actually not one equation. There are infinitely many, because this equation has to be true for all x. I could even write it just to make sure you see this. For all x, this has to hold. And that gives us the possibility to try to solve what a and b should be such that this equality holds. By the way, why would you want to do it? Well, the nice thing is once we can split this integrand like that, the integral of this and this I can do. It's just ln of x minus 8 times a. So once I have this splitting, life will be a breeze over here. Okay, so this is our main problem for now. Once we're done with that, we're going to be very happy. Now, okay, so from here on, it's a bit of algebra. And the good idea with fractions to do, if you have fractions in your algebraic equation, is to multiply with the denominators. So here I have to multiply with x minus 8 and with x plus 3. So I'm going to multiply both by x minus 8, and I'm also going to multiply by x plus 3. Okay, or you could say multiply by x minus 8 times x plus 3. All right, what happens here? Of course here, then the whole numerator is gone, so we're just stuck with x plus 2. Okay, and there, well, the x minus 8 will deal with the x minus 8 here, so we have a, but then we still multiply with x plus 3, so we have a times x plus 3 as a result. And here, the x plus 3 will deal with this x plus 3, it's gone. And we have b left, but then we multiply still with x minus 8, and we have b times x minus 8. Now there are two ways to go from here, and I'll show them both, and you can choose your favorite. As I said, this is also true for all x. So I could in particularly, and this is a clever trick, I could in particularly fill in, suppose x equals -3. I often say -3, but you know what I mean. -3. What happens something very useful happens. Well, this will simply become -1. This, hey, it will be a times 0. That was the whole idea. So this whole term vanishes, and we're left with b times -11. And out drops my value for b. b is going to be 1/11. Ooh, that went very fast. And then another trick to find a, you will probably be able to guess it from here, is suppose x equals 8. Then you get 10 here. And, well, here you get 11 times a times 11 if you want. Do I have my, yes, that's correct. And this whole term drops out, and out rolls my a, being 10/11. Now, some of you might complain, hey, wait a minute, how can I just plop in this -3 here, where actually, if I look at the original equation, -3 is not even really allowed as a solution of this equation. I said for all x, but of course we should have excluded -3 and 8. So there's something a little bit fishy about this approach. So to please those people who would like another approach that seems more valid, let's take this approach. So this was number 1. Approach number 1. Now we have approach number 2, and indeed it's theoretically a little bit more pleasing. So let's write x plus 2 and expand on the other side. We get a times x plus 3a plus bx minus 8b, which I can rewrite a little bit as a plus b times x plus 3a minus 8b. Now, this has to be true for all x. Now, geometrically, x plus 2 actually describes a line with slope 1 and y-intercept 2. This also describes a line, and if it's true for all x that these are equal, these should be the same lines. That means that the slope and the intercept should be equal. So from this, I conclude, this should be thought of as 1 times x, right? The slope is 1. I find that a plus b must be equal to 1, and 2 must be equal to 3a minus 8b. And what I have is a system of 2 linear equations which I could try to solve. Now in this case it might be easy to just solve here for a or for b. So let's say b is 1 minus a, and then substitute this in the second system. So what do I get? I get 3a minus a times 1 minus a equals 2. And it's a bit more work, right, than the other method, but at least no one has to be awake at night about these methods. I get a minus 8 equals 2, and then I get 11a equals 10, and a equals 10/11, which is fortunately the same answer that we had before. And then b is 1 minus a, so out comes, if you combine these two, that b must be 1/11. So this method is a little bit more elaborate, and you have to solve a system of linear equations. However, it gives you the same result. And well, we got a little bit distracted, right? Because we were actually trying to integrate this thing, and there was a whole side of this board full of equations. But actually, we made a very important step, because now we know that we can decompose this integrand like that. So let's plug this lovely result in, and you get actually this integral is equal to the integral of, well, a was 10/11 divided by x minus 8, and b was 1/11 divided by x plus 3 dx. Now, this is a bit ugly, right, with a fraction in the denominator, so let's rewrite this a little bit. We get 10/11 times the integral dx x minus 8 plus the integral, 1 over 11 times the integral of 1 over x plus 3 dx. And well, these both we can do. We can do them both. Of course, they're integrated by ln, and then don't forget the absolute value sign, please. Like that. And the other one, 1 over 11 ln absolute value of x plus 3. And then this constant, which we should never forget. And there you go. And let's see, I think this is absolutely fine now. Are we fine? Let's do a final check. Yeah, this is it. So here's your final answer. And it's so generally the main steps are to decompose in such a way. You have to find the constants a and b. You have two ways to do it. Either plug in these well-chosen numbers or see it as two lines that are equal. Plug them back in, and then here you have this, this integral that then can be split as a sum, and each of them can be integrated by using ln in that way. And this, of course, you've seen it in an example now, and you have to trust me that actually this method works really in general. So a lot of success trying to apply it, and see you hopefully in the next video.